Hello students, welcome back to PH107 Quantum Physics and Applications. Today I am going to discuss wave particle duality. But before I start discussing the main topic, let me provide you the recommended readings from this book Modern Physics by Survey. If you would like to read or know more about this present topic, please go to sections 5.1 and 5.2, which are given in page 152 and 154 respectively. So far, let's recap what we have learned. So we have seen that when we want to explain photoelectric effect or Compton effect, they supports the particle nature of light. On the other hand, there are processes or phenomena like interference and diffraction which requires wave nature of light. So now we are in a kind of dilemma when the particle nature of light is valid or the wave nature of light is valid. So quantum theory gives light a more flexible nature by implying that different experimental conditions evoke either the wave or particle properties of light. In fact, both views are necessary and complementary. Now, thus, we are left with an uneasy compromise between wave and particle concepts, and at this point, we have to accept that both are necessary to explain the observed behavior of light. So, now the question is, does light consist of waves or particles? So here I am going to write down the phenomena, and then in this column I am going to say whether this phenomena is explained by invoking wave nature or the particle nature of light. So let's first go to reflection. Reflection can be described successfully either the wave or particle nature of light. Refraction, only the wave nature is important. Particle nature does not support refraction. Now if you go to the interference, wave nature is explaining the interference process or phenomena, and the particle nature is not supporting. Diffraction, again wave nature, not the particle nature. Polarization, wave nature, not the particle nature. Now here is a photoelectric effect that you have seen in the previous lectures, that wave nature is not applicable to describe the observations in photoelectric effect. So the particle nature is appropriate to explain the observation, and the same is applicable to the Compton effect. So from the Compton effect, what we have learned for a photon, which is a particle, it has a momentum, and this momentum is given by P is equal to h nu over c, where nu is the frequency of your light, or h over lambda, where lambda is the wavelength of light. Now it is obvious at this point from the mathematical point of view that if you exchange P over here and lambda over here like this, so now you can write down lambda is equal to h by P. And there is no problem at all because you have just made a very simple mathematical rearrangement. However, this simple rearrangement has a very deep implication in quantum physics. That's what we are going to discuss. So it is not only a mathematical rearrangement of these two variable, momentum and the wavelength, but it also tells you very interesting and deep concept in quantum physics, and I'm going to show in this particular lecture that this particular arrangement has long-lasting consequences in current and upcoming technologies also. So Louis Treboy, around 1923-24, he said that this arrangement, what we have seen in the previous slide, that lambda is equal to h by p, is true. And what it means that while people are struggling with the dual nature of radiation or light, whether the light is particles or wave, Treboy jumped in and made the situation more complicated, or maybe he has made the situation more simplified and more unified, I would say. So what he said, if waves behave like particles, then why can't particles behave like waves? So he just implied other way around. So classically, we always think that massive objects, which are the particles such as protons, electrons are particles, and electromagnetic radiations are wave. So in de Broglie's point of view, both of these should have both particle and wave nature. So what we have seen in the case of electromagnetic radiation, that electromagnetic radiation behaves like a particle as well as the wave. So then he said that why not the particles like proton, electrons, neutrons also, which are particles, must behave like a wave. And that's what the dual hypothesis that Treboy has put forward. So this is very surprising at that time, that massive objects occupy well-defined position in space. So once you say that my object is at position X, so you know that it's a very well-defined position in space at a given instant. How they can behave like a wave? Because wave does not have a very well-defined position. So how this very contradictory statement or contradictory concept can be acceptable at this point, that electron which has a very well-defined or any particle which has a very well-defined position at a given instant can behave like a wave, and then the meaning of the well-defined position is completely lost. So let's go into more about the wave-particle duality. So in 1923, what de Broglie proposed, that if waves behave like particles, then why not particles behave like wave? That's what I have reiterated in the previous slides. We know that everything, whether it's matter or radiation, has both wave and particle properties. Now the question is, which property you see depends on the experimental conditions that you want to perform, or what kind of experiment you want to perform. So for example, for a photon, we know that photon has a momentum p, which is h by lambda. That's what we have seen in the previous lectures, also in the previous slide. Now for a particular case of a particle, let's say a particle of momentum p, now we can assign a wavelength to a particle with momentum p is lambda, and now I'm going to put a subscript dv which corresponds to Debye, and now by using this rearrangement I can write down h over p, and now my p is a momentum which is written as mass times velocity. So now here I can say that a particle with a momentum p has a wavelength which is the Debye wavelength, and which is given by h over p or h over mb. So to make more compelling argument or more compelling hypothesis, what Debye did, Debye tried to connect his hypothesis with the Bohr theory that we have seen in earlier lectures, that Bohr provided quantization of energy in hydrogen atom. So how he has put forward his hypothesis and how he has connected with the Bohr quantization condition. So one of the Bohr's assumptions concerning hydrogen atom model was that the atoms are in stationary states and the angular momentum is quantized, and this angular momentum is written in units of h or h cross. H cross is h divided by 2 pi, and we know that angular momentum can be written as momentum or mass times velocity times distance r. We will see what is distance r here, and this is the mass of the electron. So before I go into detail, let me see what you have learned in your 11th and 12th standard textbook. So this is the picture again I have taken from your textbook, and here it is written that Bohr's second postulates define these stable orbits where electrons are revolving, and he said that the angular momentum of the orbiting electron is quantized, and this is quantized, as I said, that L is equal to n times h cross or h divided by 2 pi, and for any nth orbit we can write down this Ln is equal to m times Vn times Rn. Okay, and this is the arrangement that Debye has made. So we can rewrite this mvr. Now mv is your momentum, so I can write down this p times r. Now p is your h by lambda. That's what we have seen in the early slides. So now I can write down this h over lambda times r, and here I have rewritten nh divided by 2 pi. So now h and h from this side get cancel it out. Now this lambda goes to this n, and this r combined with this 2 pi, so we can write down this n times lambda is equal to 2 pi r, and because this connection was made by the Debye, so I can write down this Debye wavelength. And this is the picture I have taken from your 12th chapter, and what Debye has said, that orbits are stable if the circumference, this is 2 pi r, this is the circumference, contains integer multiples of the Debye wavelength. So this is how he has made a connection between his hypothesis and the Bohr model, and he said only those orbits are stable whose circumference are integer multiple of the Debye wavelength. And furthermore, he stressed that the regions between the orbits could not be occupied, so electrons can only be found in a given orbit or certain orbits, not in between them, because these circumferences are not the integer multiple of the Debye wavelength. So that's what he said, that the regions between the orbits could not be occupied because a whole number of waves would not fit into this relation. So here is first quiz that you need to answer. If we use Debye wave condition, then why the energy levels in hydrogen atom are separated? So now let me go further into Debye hypothesis. So I'm sure you know this guy. This picture is quite famous. So here is Geoff Archer, and now he's throwing the ball with the speed 145 km per hour. And let's assume the mass of the cricket ball is 163 gram. So now we can easily estimate that the Debye wavelength of this cricket ball is around 10 to the power minus 34 meter. So here is a simple calculation what I have told just now. Now we know that Debye wavelength is h over mv. The mass I have given you. The speed I have converted from kilometer per hour to the meter per second. Here I have substituted. I know that what is the value of h. So once I substitute all these value, I will get something 10 to the power minus 34 meter, which is a very, very tiny number. Now if you go to microscopic world instead of the macroscopic world, so let's say we have an electron which is moving with speed 5.9 into 10 to the power 6 meter per second. Now I substitute the mass of the electron, which is 9.11 into 10 to the power minus 31 kg, and here is the speed given in meter per second. And once I substitute everything properly and calculate it, what I will get Debye wavelength is of the order of 10 to the power minus 10, which is much I would say larger value is compared to this value. So what it means that when you are in the microscopic world, the Debye wavelength becomes a very meaningful value or meaningful quantity. So we know that the atomic dimensions are the order of angstrom, 10 to the power minus 10 meter, whereas the nuclear dimensions are of the order of 10 to the power minus 14 meter, or what we call as a Fermi meter. So what we have just seen, that Debye wavelength is negligibly small for macroscopic objects, whereas the Debye wavelength is important for microscopic objects like electron. Objects that are large in the absolute sense have the property that the Debye wavelength associated with them are completely negligible compared to their size. That's what we have seen in the case of cricket ball. Therefore, large particles only manifest particle nature. Now, before I go into discussing and how the hypothesis of the Debye got validated by different experimentalists, let me re-emphasize that what we have seen in the beginning of this lecture, that if you say that any object is behaving like a wave, then that object or that wave property associated with that object must exhibit at least two kinds of phenomena. One is the interference and another is the diffraction phenomena. So let's see how the interference phenomena was exhibited by the light, which is considered as electromagnetic wave. So here is your double slit experiment, and here is the two slits. The separation between the two slits are D, And when the light falls on this one, you start getting the bright and dark interference fringes at the detector, which is at distance L. So now if you estimate, which you have done it in your earlier classes, what is the path difference of the light when it is going from S1 or S2 hole, it's given by the delta, and then it's easy to see that this delta is d times sine theta. D is the distance between the two slits, and theta is the this particular angle in this projection. So we know that the condition for a constructive interference, when you get a bright fringes, this path difference supposed to be n times lambda, which is d sine theta, this path difference. Whereas for the destructive interference, this quantity is supposed to be n plus half lambda. So what I'm trying to say that this double slit experiment can be seen by the visual light, which you have most probably done this kind of experiment in your 10+2 labels. Now another important question is that can we see young double slit kind of interference processes for a shorter wavelength? For example, for the X-rays, which you have seen are very important part of the electromagnetic radiation in the case of the Compton effect. There is another thing that was very clear to the scientist at that time, that if you want to get a very clear fringes in the detector and not any overlapping or blur fringes, then what you need to do, instead of using double slit, you can use multiple slit, so that you will have more probability of constructive or destructive interference, or let's say more paths for the constructive and destructive interference, and in this way you will get a sharp peaks here, here, here. So that's what here I have shown you, that you have multiple slit instead of two slit, and when you shine the light on that one, you get very, very bright fringes and almost dark fringes, and there is no overlapping or blurred image. And what we have seen in the previous slide and in this slide also, that your n lambda is equal to d sine theta, where n lambda is your conditions for your constructive interference are getting these bright fringes. Now if you want to go to X-ray regime and get this kind of bright fringes, this condition that we have seen in this slide, that if you want to get a bright fringes, your distance between the slit must be comparable to the wavelength. So we know that when you are going into the X-ray regime, the wavelength is of the order of angstrom. So how you are going to make this kind of multi-slit arrangement where the separation between these holes are of the order of angstrom. So of course nature has given you this opportunity. So if you take a crystal, so this is the crystal plane, and these are your atoms in this particular crystal plane, which are the distance between the two crystal planes is given by d here. Now here is your incident X-ray. It interact here and it goes like this. Now another part goes here, it goes like this. So it diffract after interacting with your crystal. Now this is the plane or the angle at which your X-ray is making angle theta. And if you draw up a normal from this point to here, this point to here, to calculate the path difference, that what we have seen in the case of young double slit experiment, then this angle also becomes a theta. Then it is pretty trivial to calculate what is the path difference. So here is the path difference will be AB plus BC, that is the path difference, and this path difference must be of the order of n lambda if you want to see the bright spot in the detector. We know that AB is your, this is your D, so this is d sine theta, BC is also d sine theta. So what you are going to get is 2d sine theta is equal to n lambda, and this is what is called Bragg's equations or Bragg's relation, where n is the order of your diffraction. That's what we have seen, and the spacing between the two interlayer in your solid or crystal is of the order of wavelength. So wavelength is of the order of spacing. So the typical spacing in your crystals or solids is of the order of 0.2 to 0.3 nanometer, which I emphasized that the X-ray with wavelength ranging from 0.01 to 10 nanometer are suitable to resolve the positions of atoms in your crystal, and that's how you are able to know what is the constituents or what are the components by which this crystal is made of. Here is a kind of supplementary information for you, and maybe you have learned, otherwise you will learn in your higher classes. So let's say this is a crystal and this is what is called 001 plane. This is 100 plane. So these are different planes, and these indices, which is written in 3 numbers, are called Miller indices in a cubic crystal, and there are different possible planes. And if you perform X-ray diffraction experiment, for example in the case of sodium chloride, then you will see these are the peaks, in your detector after performing the X-ray diffraction, which corresponds to different Miller index at different planes of your crystal. So now, after Draboy has put this hypothesis, Davison and Germer in 1927 attempted to see whether the electrons can also exhibit the diffraction pattern or not. So what they did, they took a nickel. So here is the symbolic representation of nickel atoms, and the spacing between the two lattice planes are given by D. And here are the electron beams going, and it interact or hits the nickel crystal, and then it diffract. And we know that the condition of the constructive interference given by the Bragg is n lambda is equal to 2d sine theta. So electrons were diffracted from a nickel crystal, similar like X-ray, and the diffraction peak satisfied the Bragg conditions. So what was the Bragg condition? What we have seen, I have written 1 over lambda is equal to n divided by 2d sine theta. So I have rearranged this equation into this following fashion. I know also 1 over lambda can be written as momentum divided by h. I know momentum is related to the energy of your electron, because your electrons are free. So total energy of your free electrons is written in terms of the momentum as p square by 2m. So your p will be square root of 2m times E. And now this E I can write down in terms of the voltage or the potential. Okay, and here is your signal that you have obtained after performing the electron diffraction. So here is your square root of the accelerating voltage by which you are accelerating the electrons to diffract from the nickel crystal, and here is the intensity, and these are the different peaks, what similar like what you have seen in the case of sodium chloride. So lambda is the electron wavelength. This is the Bragg's law, as I said. This is the Draboy relationship, and this is the acceleration through voltage V. That's what you have got it. So this is the condition that we have established between the Draboy wavelength and the accelerating voltage. And now if you take a Draboy wavelength is around 1.67 angstrom, which is written in terms of the meter, then you need 54 electron volt to obtain or to get this Draboy wavelength, which is sufficient to obtain the distance between the two atoms in nickel crystal, and the results what they have obtained, the distance between the two atoms in nickel crystal, was same as others have obtained the distance between the two atoms in nickel crystal by X-ray diffraction. So in this way it was established that indeed electron is behaving in a similar way what your X-ray is behaving, and both are giving a similar result for a given system, in this particular case nickel. So this is the Bragg law that I have said. So that's what we have emphasized, that your lambda should be of the order of d to resolve the distance between the two atoms. Now this conclusion or this relation, what it has been established by Davison and Germer in Bell Labs to establish that electrons indeed behave like a wave, and they can be used to obtain the structural information of your crystal, and they have set up a relation between what wavelength you want to obtain. It depends on what is the accelerating voltage that you want to that you need to apply, and in this way you can obtain what should be the D, And this concept was further used to build a microscope. So in microscope, what you need a resolution of the order of lambda, and if you get a shorter lambda, it means that you are going to get a better resolution. And this is how the let's say the electron microscope came into existence. So what is the relation between wavelength and the size that you can resolve? So let's say with a visible light, which has a wavelength of the order of hundreds of nanometer, we are limited to being able to resolve objects which are at least, as I said, that zero 0.5 into 10 to the power minus 6 meter, which is around micron size, or 500 nanometer, because this is the typical wavelength of your visual light. Now, if you follow this argument, then it means that because of the visual light wavelength, which is of the order of 500 nanometer, we cannot resolve or we cannot get a better picture with better resolution or higher resolution using this particular wavelength. Okay, so either you need to go to the shorter wavelength of the lights, like X-rays, or you can also use electrons. So here is the picture of bacteria viewed using the visual light in microscope, and this is a picture which you can see a better resolution, and here you can see a more detailed information where you can obtain more detailed information about the bacteria using the electron microscope. So Ernest Ruska and others argued that if electrons behave like waves, then it should be possible to focus electrons beam like light. Like light you can focus using lenses, the same way electrons are behaving like waves, so we can focus electron beam like we could do light. And for that purpose they designed magnetic lenses which could focus the electron waves and creates what is called transmission electron microscope, or TEM, in 1931. Electron microscope allow us to see things much smaller than typical optical microscope, what I have shown in the previous slide, which permits because this is possible because the wavelength of the electrons is much shorter than that photons of the visible light. So in principle it can provide magnification factors of 1,000,000, and for that discovery Ruska got a Nobel Prize in 1986. Let's learn more about electron microscope. The electron microscope is a device which uses the wave behavior of electron to make images which are otherwise too small for visual light. That's what we have seen. The best optical microscope using UV light have magnification of 2000. So you can only magnify this image using UV light by 2000 times, and the resolution is of the order of 100 nanometer. However, electron microscope using 100 kilo electron volt electrons have magnification of as much as 10 to the power 7 and resolution of 0.2 nanometer. So you see that instead of limiting yourself by 100 nanometer, you can go down 0.2 nanometer using the electrons with high voltage. So here is a typical layout of your electron microscope. I will not go into detail, but if you use this microscope, this is the image of a bacteria, and you can see that how clean and very detailed information is visible. So high energy particles can be used to reveal the structure of matter. This is an important point or take home message at this point. The same TEM is used, and in this present day, so this is a setup from a company which is selling this TEM instrument, and here is a picture taken, for example, this SARS COVID bacteria that you all know now by this time, and you can see that all the spiky nature by which they are sticking with different biological substance, everything is very clear using transmission electron microscope. So I hope now you have realized that very so-called simple hypothesis that Debye has put forward, that electrons must behave like a wave. So in the beginning it looks like a very simple argument, but you see that how long-lasting and important consequences this simple hypothesis has, even it is affecting our day-to-day life and it's improving our understanding about nature. So what we have concluded till now, that indeed electrons we have like a wave, and Davison and Germer, and there was another guy from UK, G.P. Thompson, who also got a Nobel Prize for showing. They have shown that electrons diffract from a crystal, and so electrons are behaving like a wave. But I have told you that if an object is behaving like a wave, they must also show what is called interference phenomena. So let's see whether electron shows interference phenomena or not. So here C. Johnson from Germany in 1961 attempted to perform young double slit experiment using electrons, and for that one he tried to construct a very narrow slits and using relatively large distance between the slits and the observation scheme, and this experiment demonstrated that precisely the same behavior occurs for both light as well as the electron. So here is the Claus-Johnson's results, and you can see that when he has two slits you do see interference processes, and when you have three slits you see more clear or more distinct separation between the dark and bright fringes. That's what I have argued in the beginning, that if you have more and more slits, then your picture will be more contrast. So the contrast between the bright and dark fringes will be more prominent. The ultimate experiment or the final establishment came when Akira Tonomura and co-workers have performed a very important experiments where they have clearly showed that electrons are showing interference phenomena, and this is the setup that they have used to perform the experiment. And these are different snapshots by which what they have done, they have collected each electrons coming out from the double slit at the detector, and they have seen as the number of electrons hitting the detector more and more, the fringes, the visibility of the fringes more and more. So they have seen, or you could say that they have filmed how the interference fringes are building up. Okay, so let me play the video before I conclude today's lecture. So here is a video. So here you could see that the interference fringes are hitting the detector, electrons are hitting the detector, and electrons are sent out only occasionally. Therefore, the chances of finding one electron in the microscope is very small, not to mention the chance of finding two. And if you see that if you keep doing the same process over and over again, you could see that you are getting more and more spots in the detector. So now you can see that the interference fringes are very cleanly visible. So you can play this video by yourself to watch it more and more times, or you can Google it. This is called Tonomura experiment, which finally established the fact that electrons indeed exhibit interference phenomena, and we have seen that electrons behave diffraction phenomena also. So there is no doubt to say that electrons are behaving like a wave. So now you may ask, is it only the fundamental particles like electrons, neutrons are behaving like a wave, or is there any size limit? So this is the question that has been asked by a guy called Marcus Arndt from Vienna in Austria, and he said that what is the maximum size up to which we can see the wave nature of object. So what he did, he took C60, this is called the buckyball or the fluorine, and he passed through this double slit experiment, and he starts seeing the interference phenomena. So it does not depends on the size, but it depends on the conditions under which you are performing the experiment. So indeed, not only the fundamental particles, but molecules such as C60 are also behaving like a wave. Okay, so this is a schematic that Marcus has presented, that you send a buckyball and then it passes through the double slit and you do see interference fringe.